Oh no, why?
Okay, welcome to our August What Happens to an Atom When Somebody Looks Ask a Physicist. For those of you who have not joined us before, we will take audience questions towards the end of the hour, but you can feel free to ask them at any time. Just use the Q&A feature at the bottom of your screen. This webinar is being recorded and we will put it on YouTube. So if you would like to rewatch it or share it with someone who you think would be interested, please do so. Lastly, our next Ask the Physicist will be September 26th, and we will have a guest presenter, ASU physics professor Cindy Keeler, and the topic is what is space-time? So with that, I will hand it over to our Beyond Center Deputy Director and moderator for the evening, Sara Walker.
Thank you, Jessica. And thanks everyone for coming tonight. We're really excited about tonight's discussion with two experts in this area. For those that are new to the Beyond Center and our events, welcome. We are a very forward-thinking center that likes to push the boundaries of science, and we're not afraid of healthy debate to advance the frontier. And so we're going to be talking about whether an atom is there when somebody looks this evening. And so you probably all wonder about what that question even means. So Paul Davies, who is our director at the Beyond Center and a very distinguished scientist who has thought about these things for many years, is going to give us the foundations. So Paul, I'm going to pass it over to you, and then we'll go to Maulik after. Thank you. Oh, you're muted, Paul.
Is Paul Davies there when nobody's looking?
I know, I was going to say, it doesn't work when no one's paying attention.
So let me start by saying the famous quote of Einstein, does the moon still exist if nobody looks? It seems like a sort of crazy question for a scientist to ask. But the whole scientific program is predicated on the idea that there is some sort of world out there, and that it exists in a certain state, and tomorrow it may be in a different state, but that there is some reality to that. There's something outside of ourselves. And most people just accept that on a daily basis. And what I'm going to do is try to share my screen now. Here we go. Things like tables and chairs around us seem to really exist. They seem sort of solid. And most people don't imagine that if you go to another room, they somehow don't exist anymore, or vanish. But then things begin to go wrong when you zoom in into the wood. In this case, zoom more and more and more. If you keep zooming, you get down to the level of atoms. And that's where things start to get a bit murky, quite literally, and the atom is represented as murky because although in the familiar international symbol for atoms, it looks like the electrons are on definite orbits going around in a definite direction. That really isn't the way it is. And this whole field is called quantum mechanics. This is the pesky subject that really threw our notion of reality into the melting pot in the 1920s. And 100 years on, people are still debating what does it all mean. Now, if you know anything at all about quantum mechanics, you'll know that it's based on something called Heisenberg's uncertainty principle. Here he is, looking very cheerful about it. And what it really means is that at the level of atoms and molecules, if we take a particle, say an electron, then it's possible to measure the position of the electron. It's possible to measure the momentum of the electron, but you can't do the same together. There's always an uncertainty in one if you have precision over the other. There's a trade-off. And that, the equation that you see on the screen is the encapsulation of that uncertainty. So if you know more of one, you know less of the other. You can't know both together. And so that, of course, raises the question about does an electron or an atom or whatever it is you're measuring know how it's moving and where it's located at the same time? Or is this something intrinsic to nature itself and not not just due to the clumsiness of human intervention. Well, if there's uncertainty, then there is indeterminism. For example, if you fire an electron at an atom, it may bounce to the left or it may bounce to the right. Quantum mechanics, Heisenberg's uncertainty, says that we can't generally say in advance which it's going to do. You might work out the betting odds. You could say it's 50-50 of going to the left or the right, but you can't know until it's happened. And then you can look and see, well, this time it went to the right, next time it went to the left. And so that means that according to quantum mechanics, nature is not only uncertain, but indeterministic. It means that you can set up an experiment, fire the electron, bounces to the left, do the same experiment again under identical conditions, bounces to the right next time. You simply just don't know what it's going to do. So there is an indeterminism. And if that's true of individual collisions like this, it's clearly true of the world as a whole. From one moment to the next, there's uncertainty about what is going to happen. And we don't notice that in daily life because the effects that I'm talking about are really very tiny in the everyday world. And it's not clear that they even apply in the everyday world, but down at the level of atoms and molecules, they're very conspicuous. Now, of course, we're familiar with uncertainty. You toss a coin, it may come down heads, may come down tails. And if you do that randomly, after a large number of trials, you'll have about half heads, half tails. And you could represent that by ones and zeros, if you like. But if you toss a coin and don't look, nobody would say, well, the coin doesn't know whether it's heads or tails. You suppose that it really is either heads or tails. You may not know until you look. So there may be some uncertainty over your knowledge, but we wouldn't say there's an uncertainty over the fact of the matter. We'd say it is in a heads or a tails state. But in quantum mechanics, we have things called superpositions. So a coin can be in a superposition of heads and tails at the same time. It might be half heads, half tails in a sort of ghostly hybrid state. And it can be any admixture. It might be mostly heads and a little bit of tails, or mostly tails and a little bit of heads. And it's even creepier than that because when you do the theory properly, these are weighted, this admixture is weighted by not just real numbers, but by complex numbers. And so that makes the nature of uncertainty at the quantum level quite different from that of tossing coins or playing roulette. Now, of course, we don't notice this if we actually conduct an experiment. We could actually take a look and see. Obviously, with the coin, you can just look in a normal way, heads or tails. But down at the atomic level, it might be spin up or spin down. An electron spin up or spin down. Could be in a superposition of those two states. You can do a measurement and you find, yes, it's in a particular spin state, or where is the electron located? Can you find it? Yes, you can do an experiment and you can pin down where it is. So when we actually look to see, we get a definite outcome. We never see this sort of ghostly hybrid reality. We never see the equivalent on the atomic level of the heads, tails together when you actually do a measurement to look. Now, what that seems to imply is that carrying out a measurement, informally we'll say looking, somehow converts that superposition into a concrete, definite state. It projects from that hybrid reality a single, unique, concrete reality, that the electron is definitely here, or its spin is definitely up, something of that sort. So that looks a bit creepy because it makes it seem as if somehow the observer is intruding into the nature of reality at the quantum level. And what exactly is it about the observation process that projects out that single world, the unique world, from this ghostly superposition of contending realities? Now, if you're disturbed by this, if you're familiar with quantum mechanics, you'll be familiar with the problem. But if you're not, you probably think this all sounds very murky. And Niels Bohr was famous for saying that anyone who's not shocked by quantum mechanics hasn't understood it. And he was one of the architects in the 1930s of one of the interpretations of this formalism. Now, not everybody liked quantum mechanics. Einstein famously said God does not play dice with the universe. He refused to believe that there is an intrinsic indeterminism or uncertainty in nature. But all of the experiments show that Einstein was wrong, that there really is such an uncertainty or indeterminism. So what do we do about it? How do we incorporate it into our notion of reality? Well, just recently, this famous actress, Olivia Newton-John, sadly died. She was an Australian actress from over many years. And why am I telling you this? Well, she's famous not only from being a superstar, but her grandfather, Max Born, was the person who worked out what you do about this uncertainty and how you give the betting odds from any particular experimental setup. And this is known as the Born rule. He proposed it in 1926. And I don't normally like showing any equations at these Ask a Physicist events, but I'm just going to put this up. What Born was effectively saying is that if nobody looks, the state, the quantum state, which is represented here by the symbol on the left, and T is the time, evolves. It just sort of goes on its own. We say it's a unitary evolution. It just chugs along, obeying a well-defined equation. But if somebody looks, there's a dramatically different outcome that instead of evolving in that manner in the top equation, the state of the quantum system is projected into one particular special state, like spin of the electron up or something, or particular energy level. And so there's a very different type of evolution that takes place, whether nobody's looking or whether somebody looks or makes a measurement. Now, of course, that's all very peculiar because measuring apparatus and a human being is made up of atoms. And so you would think, well, if the bigger system is made of atoms, surely it is too subject to this quantum uncertainty. And John von Neumann analyzed the measuring process by mathematically coupling some measuring apparatus to an atom. And what he showed was that, sure, the effect of coupling it to that apparatus is to project the atom into a particular either or state, not a hybrid of both, but either one or the other. But the price to be paid was that the entire system, that is the measuring apparatus plus the atom itself, was in a superposition of alternative realities. So then you come along with another measuring apparatus and measure the first one. And sure enough, that projects the first one into a definite state. It might be the pointer, it might be a pointer over here instead of over there. But now the bigger system is in a superposition. And so it goes on. And von Neumann thought that the entry of the result into the mind of the experimenter or the lab technician or whatever it was the determining factor of changing a superposition to a definite state. Well, that led to all sorts of problems. For example, there's the famous Schrodinger Cat Problem. You put a cat in a box. There's a radioactive substance which is subject to quantum effects. If the atom decays, then the ball drops, smashes the cyanide and kills poor little pussycat. There we are. But given that the quantum system can be in a superposition, then we're to suppose that in the box as a whole, treating it as the entire box and its contents as a quantum system, the cat is both alive and dead in a superposition, a hybrid reality of both things. And that seems sort of absurd. And it would be absurd if you decided that a cat was good enough to project out the reality. Sometimes people say collapse the wave function is the term that they use. And so it leads to this sort of notion that if the buck doesn't stop anywhere, maybe the whole universe is in a superposition of different states. And that brings me to the concluding point that all these people here seem to think, and these were distinguished physicists several decades ago, they all seem to think that somehow quantum mechanics and observation were related, and somehow free will or the mind or something like that intrudes into it. But that's very unfashionable these days, and it became particularly unfashionable in the 1980s with the development of quantum cosmology, that is, applying quantum mechanics to the universe as a whole. We know the universe began with a Big Bang. It seems that was a quantum event. And the quantum mechanics has never gone away. Vast though the universe is, it would still apply to the totality. And this is one of the recent pictures from James Webb Space Telescope. So people who work in quantum cosmology, I think, don't like the idea of the chain of explanation terminating in the mind of the experimenter, but want it to encompass the universe as a whole. And so at this point, I'm going to hand over to Maulik, who I think is prepared to defend that position. But I should say right away that there's probably about 6 or 7 different ways of interpreting quantum mechanics, and no general agreement in the physics community about which one is the right one. And so we'll have a bit of a discussion after Maulik has finished. So over to you.
And while Maulik is getting set up, I just want to invite everyone to continue asking questions. We're seeing a lot of great questions coming in the chat, and we'll be addressing those after Maulik provides his perspective on the question of this evening.
So let me see how this works. Okay, can you first of all hear me?
Yes. And we can see your screen, but the slides aren't full screen yet. There you go. Perfect.
Okay, great. All right. So what happens to an atom when somebody looks? That's the subject of today's talk. And it's about quantum mechanics, of course. And I want to start by telling you a little bit about the status of quantum mechanics in physics. Quantum mechanics is not just some exotic fringe theory that describes only atoms. It's really the most foundational theory, foundational framework of modern physics today. I think by my count, no less than 40 Nobel Prizes have been given to work that had something to do with quantum mechanics. Quantum mechanics explains not only atoms, but why we don't, fall through solid objects, how lasers work, and even, amazingly, the birth and structure of galaxies in the universe. Okay, so let's, however, focus on an atom. Here is a picture of a hydrogen atom. So already this might seem a little like an odd kind of picture to you, because you might, in school, we learned that a hydrogen atom, which is one of the simplest atoms, is basically a proton with an electron. And I've added a little blob at the center that represents the proton, the nucleus of the hydrogen atom. But the electron, unlike what you sort of see in school, where there's a kind of a mini solar system with the electron orbiting the proton, is instead represented by a cloud. So there's this beautiful, colorful cloud, never mind what the colors mean, but what is all this? So first of all, hydrogen has only one electron. So why is there this smeared out cloud? What does it represent? Well, the cloud, it's not that the electron is spread out over this whole space. The electron is just a point particle. What this cloud represents is something amazing. It represents probabilities. And this means that, well, wherever the colors are brightest, that's where the electron is most likely to be found. And wherever it's dark, that's where you're unlikely to find the electron. So instead of the electron sort of going around in a predictable way around the proton, what happens is it just exists in this haze of possibilities, a haze of probabilities. And it means that if you actually ask, where is the electron, and you do an experiment, you're going to get different results. If in experiment 1, you might find that the electron is here, and in experiment 2, somewhere else, and so on. And so we already have a very strange situation where you have identically prepared systems, many different hydrogen atoms, say, and yet when you repeat the experiment, you don't get the same result again. That's already contradicts what usually happens in science, where you want to have an experiment that is repeatable and that gives you the same result. And here, it's a hallmark of quantum mechanics that if you do the same experiment multiple times, you won't get the same results. So what does it mean that the electron is flitting around and found in different places? Well, you might be tempted to say, well, maybe we don't really know where the electron is, and it's sort of doing some complicated motion, and every time you look, it's somewhere else. It's sort of like a dancer in viewed under a stroboscope. At a disco, you see flashing lights, and each time the dancer's in a slightly different position. That's not actually what happens there. So let me tell you a bit about probability and chance. So we're used to the idea of probabilities. They don't seem so exotic. You have a coin toss. There's a 50-50 chance of it having heads or tails. We're used to the weather being uncertain and you could say there's a 30% chance of rain tomorrow. Well, we're in Arizona, so maybe more like 2%. And then there's even something, even some randomness that comes from something called chaos theory. But all these things are quite different. In the case of a coin, the reason the coin seems probabilistic is because we're not really keeping track of all the variables that would precisely determine the motion. If you knew exactly how you flicked the coin and if you knew what the air was like and what the weight distribution in the coin was, you would be able to 100% predict whether it would land heads or tails. So there's no real fundamental uncertainty in a coin toss. And the origins of probabilities there is just, the origin of chance is just because we have incomplete information. So you might think that, well, maybe the same is true in quantum mechanics, but you can actually show, and we can prove that at least it seems to us that quantum mechanics is not an incomplete theory, that it is really a completely self-contained description of the electron, and we're not missing anything. If that's the case, then an electron is fundamentally probabilistic. It's not that we're missing some information that's preventing us from predicting where it really is. It's just that it's inherently probabilistic. When we are not looking, it simply does not have a location. So, and I want to say that this is not just some philosophical description that we've imposed on this. The idea that an electron can be in multiple positions at the same time is actually the basis of quantum computing. In quantum computing, we have these computers which we now actually have. We have some basic simple quantum computers that we've now created, in which the computer takes every possible input at once. And that's because its input is a quantum object that lives in, that simultaneously exists in different realities. Okay, so the question we want to ask though is that, well, we want to explain this experiment. If the electron is really in this haze of probabilities, then how come every time we measure, it's here or here or here or here, right? Every time we actually measure, it looks like it's somewhere. It reminds me of a little bit of that game that babies play, when they play peekaboo. So every time they look, their parent is still around, and this in child psychology, it's called object permanence, where the baby sort of learns that even when they're not seeing the parent still exists. Well, that's not true in quantum mechanics. In quantum mechanics, when you're not looking, your parent doesn't exist. They could be anywhere. Okay, so we still need to explain how it is that when we do look, it's somewhere. And the original idea behind this was something called the Copenhagen Interpretation. And it's here we see Niels Bohr looking a little bit like Dracula in this picture, who was a Danish physicist. And his idea was, well, the act of observation forces the electron to choose one out of its many possibilities. So the electron lives in this haze of possibilities. And then every time you look, it's here or here or here. The act of observation singles out a particular reality. However, upon closer examination, this doesn't really hold up. Because, well, what counts as an observation? So if I look at an electron, that's clearly an observation. But what if my golden retriever Louis looks at an electron? Is that still an observation? Well, Louis is pretty smart sometimes, but maybe what about if it's a mouse or even a passing coronavirus? You know, when does it count as an observation? And in fact, why are these life forms in the first place? What happens if I have a camera that's looking at the electron? Does that not count as an observation? And what if the camera is off? So it doesn't seem like we can really isolate what it means to be an observation, especially if you think of the camera example. The camera is just an object that's made itself made up of atoms. How on earth, what makes it so special that why is interaction with the atoms of the camera so privileged that it will cause the electron to pick out a particular location? It doesn't seem to make any sense. So this was the case for many decades until in 1955, Hugh Everett III came up with a brilliant alternative. And the story is that Everett at that time was a graduate student in physics, graduate student at Princeton. And you know, like many students, he was hanging out with friends and they were drinking, like college students do sometimes. And they were playing a game, kind of drinking game. Right? And so, but these are physics students. So the drinking game that they were playing was, what are the most ridiculous implications of quantum mechanics? And so when it was Hugh Everett III's turn, perhaps emboldened by the alcohol, he made a radical suggestion, a suggestion which transformed our interpretation of quantum mechanics and actually turned out to be his PhD dissertation, his PhD thesis. And the idea was very simple. It basically said that there is nothing special about an observation. The observer and the observed are both ruled by quantum mechanics. That's all it says, that there is nothing that is not quantum mechanics. Quantum mechanics is a foundational theory that describes atoms. Everybody's made up of atoms, so it applies to everybody, include the observed as well as the observer. So this innocent-looking statement has profound consequences. For one, it means that we too exist in a haze of possibility. Okay, so how does that help? Well, it turns out that when we interact with the electron, when we observe the electron, our haze of possibilities becomes correlated with the electron's haze of possibilities. So here's a picture of how that happens. So initially, there's an unobserved electron and there's you. You then go ahead and observe the electron. Well, now there are two possible realities. The electron could be at point A, in which case you will observe it at point A, or the electron could be at point B, in which case you observe it at point B. Okay, but actually both of these are happening, because remember, the electron isn't at one place or the other, it's really at both. So in a sense, there's a splitting of reality, and since you're also quantum mechanical, you split with it. So in this case, there are now, in the second line, there are now two worlds, two parallel realities, two completely different worlds, both containing an electron, both containing you. And in one of them, the electron's at point A and you observe it there, and the other one is at point B and you observe it at point B. Now, in each of these worlds, you think, aha, that's very interesting. I've done an observation of where the electron is and I found it at a point. And so you might want to know, how did that happen, given that the electron was in a superposition of different possibilities? And the answer is, there's another world out there where you found, where there was the electron was at a different point and where you're measuring it at a different point. This can continue further. There could be a random firing of a neuron in your brain. Those are also random events, and that can lead to a cascade of electrical signals that your brain will interpret as a sudden pang of hunger, sudden craving for something. So if the neuron fires in a certain way, you might have a craving for pizza. Or if it fires in a different way, you might have a craving for ice cream. And so now we have 4 worlds at this, in the third line. You see that in world 3.11, there's an electron at point A. You remember seeing it at point A, and now you have a craving for pizza because the neuron fired in a certain way. In world number 3.12, you again see remember seeing the electron at point A, but now you have a craving for ice cream, and so on. Okay, so you can see that every time there's any kind of interaction with some sort of quantum system, there's just this vast multiplication of worlds. And each one of these observers at the end, so if you look at any one of these worlds at the end, that world seems to be telling a consistent story, right? I remember seeing an electron at a certain place and I have a craving for some kind of food. It doesn't look like this person, so it really feels like there's a definite reality in each of these worlds, even though collectively there's no definite reality at all. Okay, so you might say, well, which one's the real me, right? And the answer is all of them. And I like this analogy by Hugh Everett III, who said, we can imagine an intelligent amoeba with a good memory. And so an amoeba is like a bacterium or something. So it can, with time, whenever it comes to a new world, the splitting of worlds, the amoeba itself splits into 2. And the 2 copies of the amoeba are identical copies as the parent. So they each remember exactly what the parents remembered. And they then go on in time and develop their own personal memories. But at the moment that they're spawned, they're really identical copies of the parent. And no amoeba can say, well, I'm not the real amoeba. They're all on a sort of an equivalent footing. And so that's how you should think of many worlds. There are many versions of you that are all you actually. And it's not that one of them really takes place. So it's a little bit different from the way timelines are depicted in, say, the Marvel Cinematic Universe, where there's one real reality and the other ones are just, they're all happening all the time. Okay. This has some crazy consequences. And so here's one, don't try this at home. You could have a game of quantum Russian roulette. And so what quantum Russian roulette, the way you play that is you have a coin toss, and the coin toss, it's a quantum coin, so it can be in a combination of being up or down, heads or tails. And if it's heads, you win $1 billion. And if it's tails, you die. So should you play this game? And the answer is definitely. So here's why. Because let's look at, so in world 1, there's you about to play this game of quantum Russian roulette. In world 2.1, that's the world in which the coin is heads and you win $1 billion. In world 2.2, it's tails and you die. So the next day, in world 3.11, you're rich. And in world 3.21, you don't exist at all. So the day, the following day, every version of you is a billionaire. And so you're guaranteed to be a billionaire tomorrow. Of course, in world 3.21, where you don't exist, you'll have lots of disconsolate family members and so on. But, you know, this is sort of a selfish view here, but you'll be rich in no matter what. Okay? So I want to tell you that also that this viewpoint of this kind of splitting of worlds sounds extravagant, and it is, but in a way it's not extravagant at all, because unlike the Copenhagen interpretation, which tried to differentiate between observer and observed, here we just have quantum mechanics. We just have the laws of quantum mechanics. So the proponents of many worlds criticize the other interpretations as many words, because there's just a lot of blah, 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 whereas here we just have the same equations of quantum mechanics that predict, that describe both the observer and the observed. And if you were to take a poll of physicists today and ask them what interpretation of quantum mechanics they subscribe to, the vast majority of them today now believe in the many worlds interpretation. So I'll just end with this quote from one of my favorite short story writers, Jorge Luis Borges, who was a blind Argentinian writer. The story is called The Garden of Forking Paths, and it's very much like many worlds in which there's a web of histories of timelines that together span a whole time tree. Thank you.
Excellent. Thank you. Thank you both. So we have a lot of questions in the Q&A, so I'm just going to jump right in. I thought we would start with Mayuri's question because probably a lot of other students have this burning question after these exciting talks, which is what classes or research can undergrad students pursue who are interested in quantum physics? So advice for young people from you both would be excellent.
Well, if you're an undergrad, you're lucky because every university has classes in quantum mechanics. Most of those classes are for physics majors. If you're not a physics major, there's usually a kind of there's usually some kind of survey class of modern physics, which describes not only quantum physics but also relativity, which is equally mind-blowing.
I should say for a long time, when students asked about they'd like to do research in the foundations of quantum mechanics, you usually warn them against it because it seemed like this was not a good way to make a career. And a lot of them just went off into like philosophy departments. But over the last 20 years or so, there's been a very active engagement with testing the foundations of quantum mechanics in a variety of precision experiments that use nanotechnology and clever tricks at the quantum level. And Maulik was mentioning about quantum computing. And so that's been a huge impetus to doing experiments on the foundations of quantum mechanics. So it is in fact possible to, as an undergraduate, to learn your quantum mechanics, but go and work in a lab where they really do test some of these things. And there are still tests to be done. So it's a possible career path. It's a slightly weird one, but nevertheless possible.
Great. So this question comes from Jason. It's how do all the atoms come together to project the classical world? And why do classical objects remain whether or not you are looking? Once you look away, shouldn't the wave function be reinstated again? So how do you explain classical objects?
Oh, that's a great question.
Yeah.
So it's sort of like this. If you have a single atom or a single quantum particle, there's an uncertainty to it. But if you have 2, 3, 4, or gazillions, that uncertainty becomes less and less until finally you just have the average. So the wave function of many particles becomes sharply peaked. And so even though it's still technically probabilistic, if you say that the probability of you being right here is 99.9999999%, then you basically can say that it doesn't even look like probability anymore. You can just say I'm 100% sure that I'm here. So the certainty arises when you have very many quantum particles at the same time.
Related to
related
to that was a question about do people test for quantum effects in larger and larger objects, and they certainly do. So there are these things called fullerenes, carbon-60 buckyball, it's sometimes called, and people have done experiments with superpositions of those and even more massive objects. And so there are papers being published all the time, sort of pushing the boundaries, looking for quantum uncertainty or superposition in what you would regard as mesoscopic objects. And the question we've been talking about is whether there is some sort of scale of size or length or something like that, at which the quantum world simply goes over to the classical world, not because the quantum effects have become very small, but because there's a change of the rules of the game. And the Everett interpretation said that never happens. Even the whole universe is still a quantum system, whereas I myself have always felt a bit uncomfortable about that, and feel that that's a huge extrapolation,
Mhm.
and that there might be a scale of which the quantum world turns into the classical world. But it's not physical science, because superconductors, for example, can be this big and still have quantum effects. So I don't think it's mass. I don't think it's physical science. I think it might have something to do with complexity, but that's just a conjecture. So a system sufficiently complex would have different rules of the game, and a cat, I think, would do the job. But I don't have a fully worked out theory. But of course, that is the big question that the questioner has asked: is there a point at which we could say, yes, that is definitely classical? There's one thing that we've skirted around, which is that people pay a lot of attention to what's called decoherence, which means that no atom or electron is isolated. There's a universe surrounding it, and influences from that universe, noise, if you like, is continually disrupting the unitary evolution of the wave function, which is the thing I just showed briefly, and that decoherence, disruption, is an important part of what leads to quantum systems to behave in a classical manner. But we're getting a little bit technical.
Yeah, I want to.
Yeah,
also
so,
just-
sorry, go ahead, Maulik.
Yeah, I also want to just say that that it doesn't have that large systems can be quantum mechanical. In fact, we have our best theory of the universe is something called inflation, in which the entire universe, or at least the entire observable universe, was in a quantum state at one point and early on, and the little fluctuations of that then seeded the galaxies that we see today. So so it doesn't have to be, it's not necessarily the case that just because something is big, it'll be like a classical system. It can still be a random, hazy system, even if it's the whole universe.
Yeah, so this was now addressing Neaton's question, I think, about what scale we might expect quantum effects to break down. And I also just piggybacking on Paul's point, because I work on physics of life, will say that I think there is something that happens in molecules, that there's new physical principles and they aren't necessarily quantum mechanical. And that explains some of the weirdness there. And that Paul's complexity point is probably very on point. So we have another question from Francisco, which is, does accepting the premise that the observer and observed are fundamentally quantum and exist in superposition of states necessitate many worlds? So could that assumption lead to a different interpretation of quantum mechanics, or is the end conclusion many worlds?
Well, I think many worlds is the only interpretation that you get without somehow adding something to the theory as it is. There are ways we can modify quantum mechanics. There's something called a pilot wave approach, and there's some dynamical collapse and so on. But we don't have any concrete evidence that any of those modifications are correct. So the existing theory that we have seems to lead to many worlds. Now, I should say that, and that's why it's so popular, but I should say it still leaves everybody uncomfortable, because it's hard to make sense in particular of probabilities. If everything is happening, if everything is possibly happening, then it would look like everything is happening with probability 1. So what is the meaning of these probabilities?
Yes, so as far as I know, the Born rule, which I briefly mentioned, which is the way you extract the probabilities from the wave function, it doesn't come out of the Everett interpretation. So have to add something. It isn't a natural product of the theory. And part of the reason I don't like the many universes interpretation, it's not that I've got anything against lots of universes, it's that I take consciousness seriously. I think it's a real phenomenon. I think that if science is to explain the world, we need to explain consciousness. And maybe it's got nothing to do with quantum mechanics, but it does. For about 100 years, people have felt there's a link, and it seems like there's a big missed opportunity if we just say an observer is nothing but a collection of atoms, and an observation is no more than an interaction and the observer's gone away in the Everett interpretation. There's nothing special or significant about mind. And if you take mind or consciousness seriously, then that's a missed opportunity. And so that's part of the reason I don't like it.
Maybe so, but I think you can make an observation with your iPhone that doesn't involve an observer at all. At least
Well,
not
somebody had to build
the.
the iPhone, though. I think this is kind of the misnomer there, because people say these measuring devices don't require intervention of evolved objects, but technology to do measurements doesn't exist unless it's products of evolution. So you already have to invoke whatever physics explains life and mind to even get to an iPhone.
But then that observation, the consciousness there would be something in the past. So I'm not even sure that there's that.
Right,
That
but this is why
would be a
physics of life
causal-
is different than traditional physics, because you have to account for the time for an object to come into existence.
Yeah, I would be surprised to see how that works in terms of causality. But okay.
That is how causality enters physics. That's a whole nother thing. So we have so many questions and they're all really great. There's a couple in here about free will. So one wanted to know what Many Worlds says about free will. One wants to know if you believe in free will. And then there was another one about what Heisenberg uncertainty has to say about free will. So I think you guys can choose your own adventure about addressing some of the interest in this topic and its relationship to quantum mechanics.
I don't think indeterminism helps with free will because if you believe in free will, you want your will to determine your actions. You don't want to think, well, I'd like to raise my arm, but my leg went up instead, because uncertainty or indeterminism means that anything could happen. And so I don't think quantum mechanics actually helps. But a lot of people have seized on it as opening the way to introducing free will into physics.
Maulik, what's your take?
I agree with what Paul just said. Certainly in the non-quantum world, the classical world, which is very, very deterministic and predictive, so that the future is uniquely predicted by the past, leaves no room for free will because your history already determines your destiny. But the quantum mechanics seem to offer a way out by saying that there are many different futures connected to a past. But if they're random, then really you've never had much of a say in them. So I don't think
it's only if somehow the mind can load the quantum dice and change the weights, and then that wouldn't be quantum mechanics. That's quantum mechanics plus, plus some bizarre mental construct.
I do think that we can sustain an illusion of free will. And maybe that's a topic for some.
That could be another one, another one of these series. So this might be a good clarification for a lot of people, but a friend of the Beyond Center, Thomas Hulin, asks, is the multiverse a competing theory to many worlds? How would you go about designing experiments to confirm either many worlds or multiverse? So what's the difference between those two concepts, if there is one?
Oh, that's a good question. So the word multiverse actually has two different meanings in physics, and one of them is the one we described today, in which there's sort of parallel realities, in which all of them containing you, let's say, in which you do different things. But there's another view of multiverse, which is there's one reality, and that reality contains multiple universes. There's just some other universes out there, and the evidence for that comes. Well, evidence is a grand word for that, but there's some suggestions in string theory that that's maybe the case, that you'd have a sort of a multitude of different universes where the laws of physics are maybe a little bit different in these different universes. Maybe the electron is heavier there, or maybe this place doesn't have an electron. So you could, and you don't exist in those other universes. And maybe even the laws of physics are different. So that's a different view of the word multiverse.
Great. Paul, do you have anything to add, or shall I go to the next question?
Now you could go to the next one. I did want to make one clarification, which I can do by addressing Barbara Temple's third question.
Yes.
What is an atom? Can we say what it's doing, when nobody's looking? It's important that people realize that when we say quantum mechanics means that there's uncertainty, that doesn't mean that something like an electron or an atom is unreal, or it doesn't exist when you're not observing it. It does exist, but it exists in a less than real state. If by reality you mean a sort of 19th century view, where every object would be at a place and moving with a speed, it would have a whole set of attributes. It might have a spin, it might have a color, there's a whole lot of things you might associate with it. In quantum mechanics, if you're not doing an observation, the system hasn't gone away. You put the electron is in some superposition of states, you don't bother to look. It hasn't gone away. It's just that it exists with less than the full complement of attributes that you would traditionally think of as you do in terms of tables and chairs and things like that. So it's less than real, but it's not unreal. And I think that's an important distinction.
Excellent. So this is a straightforward question, but I think probably a lot of people would benefit from the clarification. So Reginald is asking if you can explain coherence and decoherence to a 5-year-old so that people can understand that concept. Great way of putting it.
It's all about noise. I think 5-year-olds understand about noise. External disturbance, jiggling things up. It's probably best by analogy with waves on a pond. If you throw 2 stones into a smooth pond together, you get the ripples spread out and then they interfere with each other, you get a nice pattern. But now if the wind blows, that's external noise, and it messes that pattern up, scrambles all the little peaks and troughs. And that's in effect what decoherence means in quantum mechanics. You have a wave-like, nice, smooth, regular wave-like patterns. Maulik was showing these colored blobs, being the electron. And if you now come at it, with some sort of ether wind or something, those blobs would get all shaken around, and then that would mess up the predictions of quantum mechanics. Don't know if a 5-year-old would understand that.
Yeah, decoherence doesn't remove the probabilities, though. It doesn't actually fundamentally eliminate the problem of explaining how there are probabilities and how you still have many worlds. What it does do is prevent you from being in some weird if you're a macroscopic object, from being in a weird superposition of being, say, dead.
Right. If you wanted Maulik here and Maulik there, that's a possible quantum state. But because of all this decohering environment, all the noise, the hybrid nature of that gets removed by either one or the other. Well, in Everett, it's both, but it's seen by different observers in different branches.
So we have another question that's kind of breaking down some technical word choices that are used but seem mystical to people, which comes from Richard, which is, can you give a simple explanation of what is meant by branch weights in many worlds interpretation of quantum mechanics? So I think this is another thing people hear all the time but don't really know what it means. So maybe you guys could explain that one as well.
Well, actually, that's a tough question because
I know.
Yeah,
that's probably why they asked it. Never quite understood it, but please help.
So that's one of the critiques of many worlds, that it's not so. Let me just explain the terminology here. So each of these universes is each of these realities, each of these worlds is considered a branch, because it's sort of there's a tree of possibilities. It starts out with one world and it splits and splits and splits, sort of like branches, creating more branches. And so those are all called branches. And then somehow the likelihood of those branches is considered, it's called the branch weight. But again, so this has to somehow match with what we measure in quantum mechanics as probabilities, but it's not really clear how to do that. Because
well, that's the Born rule again, isn't it, Maulik?
That's so that's what branch weights mean, but how they're actually connected to the probabilities of quantum mechanics is not clear in many worlds interpretation, and that's one of the critiques of the picture.
Great,
I
thank you.
noticed that, Sarah, there was a question about do you have to actually look and see, is the cat alive or dead, or is sound good enough? And
Yes,
I
that
can't
was-
resist telling you, I once did a TV show on quantum mechanics, and we thought we'd reenact Schrodinger's cat experiment. And the studio cat was the most incredibly docile creature, didn't mind being stuffed into a box. But after the 10th retake of this thing was sort of clawing like that, stuffing it down in the box. And then, of course, it was meowing and collapsing the wave function. So yes, it doesn't matter what is the physical mechanism whereby you can say the cat is alive or dead, or the electron is here or there. Anything will do in quantum mechanics. It doesn't have to be light. You don't have to
Yes,
see.
it can be any observation, not just light, sound, anything. And so if a tree falls in a forest and there's nobody there, not only in quantum mechanics, not only is it not clear if it makes any sound, but it's not clear if it fell or if it's even in the forest. So yeah.
Great. So I think we have time for about one more question. I'm just trying to think what might be the best one here because there's so many great ones. So there's some questions about, and maybe this can combine a couple, about whether many worlds theory concerns quantum information, mass, and energy. And another one was about if each event makes kind of an infinite series of new events. So maybe you can say, like, is this a continual generation of new possibilities, or is anything conserved in these processes? It seems to be kind of a running theme through several questions. This branch.
There's one clarification that David Deutsch always makes, which I think is very useful. That Maulik was showing these branches, and then you think, well, all the new universes appearing, whatever happened to conservation of energy and so on. But you don't have to think of it that way. You can just think of, there's always an infinite number of universes, and at the beginning, most of them are simply identical. And then when I showed the electron bouncing off the atom, maybe the left, maybe the right, what happens is that there were always two universes, identical. Along comes the electron, and after that, they become differentiated. One has a left-moving electron, the other right-moving electron. So you're not multiplying universes, you're just differentiating over time. Would you agree with that, Maulik?
Yes, they conserve all of the things mentioned, quantum information, mass, and energy, precisely because of what you said.
Great.
We've left you speechless, Sarah.
Yeah, I thought that one was going to take a little. We have 2 minutes left, so let's see. How about this one? Can quantum effects act on an object at a distance?
Oh, yes. Well, how long have we got for that?
I know. You have a minute.
Absolutely critical aspect of quantum mechanics is its non-locality. And so what that means, it's been known since the 30s, that you can have two particles that interact and move a long way apart. They might be light years apart. That you do an experiment on this one and an experiment on that one. And when you compare the results afterwards, you see that there is what Einstein called a spooky action at a distance. There is a correlation between them that could not be explained in any simple notion of reality. The particles really do have those attributes prior to them being measured. And so this whole set of experiments, often called de Bell type experiments, continues in various refinements. So there is this non-local, often called entanglement. It's a critical feature of quantum mechanics and one of the most exciting, baffling, and experimentally explored.
Yes, although things that are at great separation can be intimately connected to each other, and so that the fate of one immediately affects the fate of the other. Somehow, miraculously, no information can be propagated that way. So you can't use this quantum entanglement to send information faster than light.
Right, you can't do faster than light signaling. A lot of people make that mistake. They think that you can do that, but you can't use it for signal.
Excellent. Well, I want to thank you both for being excellent sports this evening and doing a phenomenal job answering the questions. And thanks to our audience, really top-notch questions. I'm sorry we couldn't get to all of them. There were a lot coming in. Clearly, this is a very exciting topic. And we hope that you'll join us again next month to find out what space-time is. And we'll have another installment where you can bring all your questions and get them answered by experts. So thank you, everyone.
Cindy Keeler and I will be talking about what is space-time and what are extra dimensions and what do quantum black holes teach us about space and time.
Excellent. Thank you.
Okay, very good. I'll say
Bye,
good night
everyone.
to everyone. Thank you for joining us.